minus tau lambda is minus that integral. So tau lambda is equal to the integral from 0 to s of kappa lambda rho ds prime. So you integrate kappa lambda rho ds prime between 0 and s, but wait, that was the integral that was up in the exponential that we were writing before.
There we go.
Yes. Mm-hmm. So, before we had said that if we don't assume that kappa lambda are rho and constant, we get that I lambda is equal to I lambda naught e to the minus that integral, 0 to s of kappa lambda rho ds prime. But that integral is tau lambda. So we have this nice expression, I lambda is equal to I lambda naught times simply e to the minus optical depth, e to the minus tau lambda. And if you take logarithms, what we find is that means that tau lambda is just the logarithm of I lambda naught over I lambda. I lambda naught's bigger than I lambda is because it was brighter at the source than it is at our location. So the natural logarithm of how many times brighter it was when it started out compared to what we see is the optical depth.
It's a ratio.
It's, yes, the logarithm of that ratio. So if tau lambda is 1 at an optical depth of 1, notice that says I lambda is I lambda naught e to the minus 1 over e. So if the optical depth is 1, a fraction 1 over e of the photons from the source is making it to us without getting scattered along the way. If the optical depth is 2, only 1 over e squared of the photons make it to us. So more like 10% of the photons, because 1 over e squared, you know, well, not quite as bad as that, but you know, 1 over e squared is 1 over 8, what's that like 1 over 8, something like that, whatever e squared is. 2.8 times 2.7 whatever squared, right? If the optical depth is 3, e to the minus 3 of the photons are reaching us. So it's an exponential relationship here.
It's decay.
Yeah, so it's right. And so the idea then is think of looking into a fog. What as somebody walks away from you in the fog, their optical depth is getting bigger and bigger, okay? And the fraction of photons that reflect off of them that actually make it to you without bouncing off of a fog particle and getting absorbed or scattered first is getting smaller and smaller. When they're standing at an optical depth of 1 away from you, only about a third of their photons are making it to you, because 1 over e is roughly a third. If they're at 2 optical depths away, only like an eighth or a ninth or whatever of their photons are making it to you, and so forth. So their optical depth is saying how clearly you can still see them. As somebody steps away into a fog, as they retreat from you, their optical depth is getting larger and larger. And the idea then is that the optical depth is in some measure, is in some sense a measure of how far you can see into an opaque gas. At an optical depth of 1, you already are only getting 1 over e of the photons from that location. And that's an idea that we're going to be making use of over and over again. I'm going to, excuse me, I'm going to finish up with just a couple of more considerations here. So we said that tau lambda is the integral from 0 to s of kappa lambda rho ds prime, but L lambda, we said, was 1 over kappa lambda rho. So in other words, we can also interpret the optical depth as being the integral from 0 to s of ds prime over L sub lambda, and that would be the number of photon mean free paths between the source and the observer. Because if I take a little distance ds and divide it by the mean free path, then that's the fraction of the mean free path that ds represents. So if I add that up all along the beam from the source to the observer, that would represent physically the number of photon mean free paths that are in between me and the source. And the bigger that is, the less photons make it to me. When the optical depth is 1, if the mean free path is constant, an optical depth of 1 corresponds to the source being 1 photon mean free path away from me, is what it comes down to. In that case, actually close to 2/3 of them don't make it to me. But the mean free path, there's no contradiction there, because remember that remaining third of the photons are going to scatter between you and infinity. So the average is biased out towards the fact that there's a small number of them that go very large distances before they scatter. And so that when all is said and done, the average distances can be equal to what it should be. I don't know how this else to put it. And yeah, I think we can stop there. But what questions do you have, just in case? So it can be on the video if you have any questions.
I'm good.
You're good? Okay. All right. So then I'm just going to go. Hi, Amanda.